Okay, this is going to be incredibly important today. So for these three symmetries, which are examples which all we really care about, look at this one. The E field is perpendicular to the plane and is constant. Here the E field is radial. Here the E field is radial. So at most, the associated E fields only depend on the radial distance. Okay? The radial distance. Keep that in your head. Okay, we talked about flux. Flux means flow. So the equation for flux for something like this is just E dot A, right? EA cos theta. So this is the maximum flux. If this were parallel to the E field lines, it would be 0. But don't forget, what's really flowing for an E field? Is there anything material flowing? No. I mean, an E field isn't made out of atoms, Okay. But then we decide to get super general. So we have this arbitrarily closed, that's important, you'll see in a minute, so closed three-dimensional surface in a non-uniform E field. We break it up into these little tiny, rectangles or squares or whatever, each delta A, and then we calculate the flux through every single one of these things, and we add them all up. And then we make these things smaller, 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 so the addition, or the sum, is just an integral. So this is that's the real equation. And again, I'm really sorry, I don't know what's the deal. Whenever I connect these things to the projector, it doesn't work properly, but it's supposed to be this. All right, so it's supposed to be a circle, and it means it's a surface integral. So you're doing the sum over the surface, right? Just as I showed you in that previous picture. So it's called a surface integral. And you'll see what that means in a few minutes. Okay, so that's the review. Any questions for the review? Or any questions? Okay. All right, so I have some questions for you. What is the net charge in this box? Positive, negative, or 0? Positive. Why? You're going to yell. Yeah, E fields are going away. Everybody agree? What is the net charge of this one inside? Negative, because? Going in. This one? Yeah, 0, right? Neutral, 0, right? This one? Positive. Okay, very good. Is the size or the shape of the object enclosing the charge important? No, who cares? There's a cylinder, there's a cube, big deal, we don't care. It's irrelevant. Okay. So there appears to be some kind of a relationship between the flux, the magnitude and the sign, and the charge enclosed by some surface, right? Would you give me that? All right, so the flux is related to the charge enclosed in the surface. Well, that relationship was proved by Gauss. So that's why we have Gauss's law. And we're going to use Gauss's law to calculate E fields in an incredibly easy way. So here is Gauss's law. Well, here's part of Gauss's law. So Gauss's law just says that the electric flux through a closed surface is equal to the charge enclosed divided by our good old constant epsilon 0. Now that's all right. That's just Gauss's law. And this is really the way you want to write it, because the flux is the surface integral E dot dA is equal to Q enclosed over epsilon 0. All right? Gauss's law right there, the bottom one. Flux integral E dot dA equals Q enclosed over epsilon 0. Now the important thing, which is kind of interesting also, it says Q enclosed. Well, enclosed in what? Well, here. The charge is enclosed in an imaginary, i.e. fake, closed surface. It's called a Gaussian surface because it's Gauss's law. Now that seems kind of weird, right? But that's how it is. So basically, we're going to have some charge. We're going to decide on some incredibly intelligent fake closed surface, and then we're going to do the integral without integrating. Does that sound like a plan? I know it doesn't make a lot of sense right now, but just hold on. Just hold on. All right. Okay, so yeah. Okay, here's a question before we do some examples. All right, ready? What is the flux, the total flux passing through the surface of that closed cylinder? Let's vote, according to Mr. Gauss anyway. Let's vote. Now let me remind you, this is Gauss's law. The flux is the charge enclosed over epsilon 0. Okay, so why don't you guys argue with each other? Please. And remember what you learned about electric field lines, yeah? Electric field lines start and end on charges. So why don't you three argue with you two? I don't know, just argue, come on. Number 1 is incorrect. Here's a big hint.
I knew that a second ago.
I know. Okay, look at the electric field lines. Is there a charge enclosed in the cylinder?
No.
So therefore, what has to be the flux?
Oh, that's not very nice.
Okay?
Fine.
I mean, that's all there is to it, okay? The flux is the charge enclosed over epsilon 0. And because of the way that these E fields are situated, there's no charge, right? Because the E field line begins or ends at a charge, so there's no charges in here. There's charges over here somewhere, there's charges over, there's charges over there somewhere, but there's no charges in that cylinder, so the flux is 0, okay? All right, that was fun. Okay, so what we're going to do now, we're going to use Gauss's law to calculate E fields. Now, something you're going to be careful. Gauss's law is only going to allow us to calculate the magnitude of the E field. We have to figure out the direction, which is usually not so difficult, right? In fact, usually it's trivial. So just remember that, magnitudes only. Okay, so here's how we're going to do it. So we have 5 problems to solve. I'm going to do the first 2, and you'll do the last 3. Okay? Sounds fair?
That doesn't seem very even.
You're right. Okay, first we're going to do a outside a charged sphere. Now remember last chapter we just kind of said, it's just a E field of a point charge, remember? But we didn't prove it. We just said that's how it is. Well, now we're going to prove it. And we're going to use Gauss's law. All right? Okay, so here's the important thing. This integral, we want to simplify it. First of all, what we want to do, so we have an E dot dA, right? That's a dot product. We don't want a dot product. We want this to become just E dA. So what does that mean about the vectors E and dA? What do they have to be if we want this to go to that? Just magnitude only. Parallel or or anti-parallel, right? Because we're not caring about the signs. Okay? So we always want that to be true. So we want the E field lines to be parallel or anti-parallel to the dA lines. And remember, don't forget. So let's say this is our A or dA. Remember, the dA line is perpendicular to the surface. Remember we learned about that? Okay. All right, so that's number one. We want to get rid of that dot product. Number two, we want the E field always to be constant on the surface so we can pull it out. So we just want to end up with something like this. All right? So we always want the E field to be constant on the surface. And who chooses the surface? Who chooses the fake Gaussian surface? We do. So we just have to be clever. We're going to just choose a surface so this is true and this is true. All right? Okay, now stare at that. Here you have this sphere. So we have to surround it by a three-dimensional closed surface. And we want to have that closed surface such that this is true and the E is constant on the surface. So what would be, and we know that the E fields of circles, planes, and what was the other one? And lines, right? They can only, wires, they can only depend on R, right? Remember that? The first slide I showed you today? Okay, so what are we going to put around this thing? I almost gave it away. I hope you guys didn't notice that. What are we going to put around this thing so this is true and this is true? A sphere. Okay, now how are we going to orient that sphere? I mean, you know, here's this sphere, right? I mean, are we going to do it like this?
Oh, I see.
So okay, so concentric, yeah?
If you want to be fancy, I guess.
So we're going to, okay. So that's how we're going to do it. We're going to use a concentric sphere. All right? Concentric sphere. Now, look at how wonderful this is. Now, notice, I'm trying to make a big deal about this. This is the sphere that we're trying to find the E field for outside, you know? This is a fake Gaussian surface, okay? Three-dimensional closed surface. Now, look. Here, you know, you're going to split up into these little tiny dAs, right? But the dA is perpendicular to the surface, and the E is what? Only radial, remember? It points radially away. So everywhere, would you agree, on the fake Gaussian surface, isn't the dA and the E, aren't they always going to be parallel? They're always going to be parallel. And look, if we make the fake surface concentric with the sphere, that means the surface is always at the same value of R. So it's going to be, what has to be true about the E field on the surface? Constant. Why? Because R is constant. And because what did we learn? One of these days I'll get there. Ta-da! At most, the E fields can only depend on R. So if R is the same, the E field has to be the same. Okay? So that's the key. All right? So that's the key. We're going to sorry. Okay? All right. That is the key. Now, are you ready to see how to integrate without integrating? I know you've all been waiting to see how to do that. Okay, here we go. Okay, so integral E dot dA. Okay, we've chosen our surface so that E is parallel to dA. So goodbye dot product, right? So now we have E dA. All right, everybody okay with the first step? Okay, then we were smart and we made the fake Gaussian surface concentric with the sphere, so the R's are all the same. So the E field has to be the same, We're talking about on the surface. So we can pull the E out. Okay. Now, remember, this is a surface integral. So you just think about the Gaussian surface, right? You're breaking up into all these little tiny dAs. This is just summing them. Okay? So what's that mean? So this is just, this is the sum of all the little surface areas. So that means it's the total surface area, right? What's the total surface area of a sphere? The total surface area of a three-dimensional sphere. 4 pi r squared? Yeah? So we just have 4 pi r squared times E. Okay? So look did I have to do one bit of integrating? You know, as you learned in first semester calc. Did I have to integrate one thing? No! Huh? But I solved an integral. All right. Now this has to be equal to Q enclosed over epsilon 0, right? According to Mr. Gauss. Well, what was Q enclosed? Just Q. Wasn't it? Just Q. So that's just equal to Q over epsilon 0. That means that the E is just Q over 4 pi epsilon 0 r squared, which is just KQ over r squared. Have you seen that before? Oh. Yeah? Yeah? All right? Isn't that wonderful? Now do you believe me? Okay, so again, here's the key. Well, here I have a slide. Here's the key. So here's Gauss's law. So we will always choose the surface so that this is either, so that the E and the dA are either parallel or perpendicular. Therefore, the only answers are going to be E dot dA is EDA or 0. That's it. Now, to make it even better, we're going to choose that the E field always to be constant. So that means we can pull it out of the integral. So that means that this funny-looking integral here is either it's going to be either 0 or EA. Always. Always. No exceptions. Is that wonderful or what? All right, now what we're going to do. Okay, all right, so I'm going to do the next one, then it's your turn. Okay, what we're going to do now is we're going to do an infinite wire. Now, you recall we did a finite wire in the previous chapter. And we had a messy integral, and we had to use integral tables, remember? And then once we got the finite wire, then we had to make it infinite, which wasn't so hard. But, I mean, the finite wire was a lot of work. Well, we're going to do this in a much easier way using Gauss's law. Are you ready? Okay, so let's do it. All right, let's see. Hold on a second. All right, here we go. Oh, sorry. No, don't do that. Choke. I don't want to give it all away. Golly. Okay, so here we have just imagine a wire. We want to choose a surface so that the E and the dA are either parallel or perpendicular, and the E is always constant on the surface. So we want to make it somewhat symmetrical, right? So if we have a wire, what would be a good surface to choose? A cylinder. So here it is. And look, we don't even have to enclose the whole wire. Just a piece of it is going to be good enough. Okay, so we have an infinite wire, linear charge density lambda, just like before. Here's a cylinder. We're going to make it concentric. Now look, so I call this the barrel because I don't know what else to call it. So I call this is an end cap, this is an end cap, and I call this the barrel, right? So look at the barrel. Would everybody agree that the DA and the E have to be parallel? You know, that kind of makes sense, right? It's radial, all right? So everywhere on the barrel, I can get rid of the dot product, and I can pull out the E from the integral. Now, what's the E dot dA on the end cap? 0. Agree? Because the E field is always radial, and on the end cap, you know, the dA always points out, so cosine of 90 is 0, right? Because the flux is 0, okay? All right, so let's do it. Okay, so here's how you do it. All right, so E dot dA. Okay, now there's 3 pieces. There's 2 end caps and there's the barrel. So, you know, this is a surface integral, so you have to do the entire surface. All right, so E dot dA, I'll say left end cap plus integral E dot dA right end cap plus integral E dot dA barrel. Okay? Okay, now, again, what is this for the left end cap? 0. What is this for the right end cap? 0. Okay, let's do this in steps, okay? So what can I do to the dot product for the barrel? Get rid of it. What can I do to the E? Pull it out, right? Because it's constant, because it's concentric. So now I just have E integral dA. Okay, this is the surface of a barrel, or a right circular cylinder, right? But no end caps. So what is the surface area of the barrel of a right circular cylinder? And the radius of this cylinder is small r, lowercase r. Okay, Adam?
I was going to say that it's the length of the surface times circumference.
Yeah. So it's 2 pi r uppercase L. By the way, uppercase L, that's the length of the fictitious Gaussian surface, right? I mean, it's fake, you know? Okay, so far so good? Any questions? All right. Now, we have to say, what is that equal to, according to Mr. Gauss? The charge enclosed over epsilon 0. Okay. Well, what's the charge enclosed? Wait a minute. Well, they didn't give us any Q. They just said that charge density is lambda. So what's the charge enclosed? What's lambda? What's the definition of lambda? Charge over length. Okay, so what's Q enclosed? What does Q enclosed have to be? Sorry? You don't mean what you're saying. You said Q over L, right? Okay, we don't know Q. We want to get Q. So we have to have a lambda somewhere, right? Lambda is charge over length, so what's the charge going to be? Lambda times what? We want to know the charge enclosed in that little cylinder. The little cylinder has a length L. So what's the charge enclosed in that little cylinder? Yeah, lambda L. Does that make sense or what? Or did somebody say it and I didn't hear you? I don't know. All right. So now we have E times 2 pi r L equals lambda L. So therefore, what's E? field, the L's go away, so we just get lambda over 2 pi r. Oh, I forgot my epsilon naught. I always forget that epsilon naught. Sorry. Yeah. Okay, lambda over 2 pi r epsilon naught. So what do you think? How long did that take compared to the other method? Okay, now let's make this a little bit nicer. When we did this the first time, I think we had it in terms of k. Remember? K is 1 over 4 pi epsilon 0. Remember that? Okay, now I'm pretty close. What do I need to do? So yeah, so 2 over 2. So now I have E equals 2 lambda 4 pi epsilon naught. So I just have 2k lambda over r. Right? Everybody? Because okay. Would you agree? Okay. So there it is. That's the answer. Whoa! All right. So, Adam, did I tell the truth at the beginning of class?
It's definitely better.
But, I mean, isn't this awesome? So, you know, okay, so let me tell you the key. Well, there's 2 keys. Number 1 is choosing the right surface to make, you know, again, what we want to always have is we want to have this. We want this dot product either to be this, or parallel or perpendicular, and we want the E to be constant. So this integral, so we're never going to have to integrate anything. This integral is always going to be 0 or EA, where A is the surface area, you know? So there's never any integral. Okay, so that's one key. The second key, which sometimes is a little challenging, but not usually, the second tough part is to figure out what Q enclosed is. Because they're never going to give us, you know, they're going to give us like lambda or eta or, you know, a rho or something like that. They're going to always give us charge densities. So we have to figure out the charge enclosed in the fake thing. All right? So this might be a little challenging sometimes. Now, something else I want to point out. Uppercase L is the length of a fake cylinder. So could the E field of a real wire depend on the length of a fake cylinder? What do you think? Does that make a bit of sense? For an E field of a real wire depend on the length of a fake cylinder? Totally ridiculous. All right? So when I had an L here, I knew it was going to go away. So I knew that the L had to be enclosed, had to be part of this Q enclosed. All right? So whenever you have something over here that's a dimension of a fake Gaussian surface, you know it has to leave, because you can't have a final answer in charge of something that's fake, you know? Okay, make sense? All right, any questions? Because you're doing the next one. Any questions? All right. Okay, your turn. Oh, I already said that. Okay, so I'd like you to please calculate the E field outside a thin, infinite, non-conducting, uniformly charged plane. So it's an infinite piece of saran wrap, okay? A charged piece of saran wrap, okay? Now I'll give you, let's just talk about it before you do all the work. What would be a good choice for a Gaussian surface? Okay, we could use a rectangle. What else could we use? Cylinder. What else could we use? A cube. Is that what you said? Okay, so either of those would be great. So the author, Randy Knight, uses a cylinder. Okay? And how are you going to orient a cylinder? So here's a piece of saran wrap. So how are you going to orient a cylinder? Yeah, like this, right? Okay. All right, go for it. And you can talk to each other, please. That would be good. So everybody figure that one out. The reason Randy Knight uses a cylinder is because we use a cylinder for the wire. And so, we're kind of used to using cylinders, so why not just use it again? So talk to each other, work together. You can push your tables together or whatever you like. Work together. You can do whatever you like.
Yeah, they like the ones online versus like this. Like there's been like a lot of like differences between them. It's a great fact.
Well, by the way, how long did it take us to do this in the previous chapter?
An entire class period.
Because we did a wire, then we did the disk, and then we did the infinite plane. Yeah.
Or should that be DA? We do this side too?
Well, I mean, A is just the sum of DAs, right?
Yeah. We could do both sides. Okay. Yeah. Can we not just multiply this by 2 because it's the camera? Whoa, look at me. Why are you laughing? Area. We find the area. No, really don't want to. It's the area of this thing, right?
About the sides of the long sides of the cylinder, just the ends.
So do we use this bit?
So it's just
So here, does this help?
just the heat
Ah.
That's what you've drawn. That's close enough. I mean, you're doing great.
So we just need to find circles, 2 circles.
So, okay, you're doing great. Keep going.
Help me.
So we need the area of the circle, so it's going to be.
Isn't there pi 2 pi r squared?
So it says area A. You can just say A, right? No, I'm sorry. On your integral,
Oh,
you have integral dA. That's the sum of the dAs. That's just A.
okay.
I mean, do you agree?
But we still have to figure out what the area is.
Yeah. Okay. Everybody see what Katie just wrote? Is everybody okay with that? Okay. I mean, because they didn't give us R right? They didn't give us a radius. They just said A, so that's okay. And remember what I said, the integral is always going to equal EA or nothing. So it's always going to do that, EA or nothing. Okay, now the trick is going to be, what is the charge in, okay, but look here though, sorry. You want to see what the charge enclosed is, you know, where the cylinder intersects the plane, right?
Okay. Would we need two, if it's only going to be EA, so we need two EA then?
Is that not just the area? We need 2 EA.
Yeah.
Like, surround.
No, you keep going, you're doing great. So what's the charge enclosed?
Wait, no.
Yeah, you're doing great. Yes, everybody agree? Because eta is a charge per area, so if you multiply that by the area of the cylinder, you get the charge enclosed. That's it. Nice going. All right, so I didn't erase this for a reason, right? So, you know, again, it's either going to be EA or 0, right? These integrals are always going to be EA or 0. So on the end cap, like everybody said, it's EA. On this end cap, it's EA. On the barrel, it's 0. So then we just have to get Q enclosed over epsilon 0, and then everybody realized that Q enclosed was just A to A, right? Charge per area times area. Okay, so we had 2 EA equals A to A over epsilon 0. The A, now why do the A's have to go? What is A? It's the, what is A? It's part of a fake cylinder, right? We can't have an E field depending on something fake. So the A had to disappear. And it disappears from the Q enclosed. So E field, eta over 2 epsilon 0. All right? So rather than spending an entire class, we spent 5 minutes. So everybody stare at that because we're going to, the next few are going to be very similar to this. Any questions? Seth, you have questions?
I'm just confused what we're finding. I thought I understood, but
Okay, kind of, what's confusing?
so like I thought we were trying to find the end bits, and then you said where they overlap. So now I'm confused.
Okay, we had, okay. So we had to evaluate this surface integral, right? We had to. You have to evaluate the entire surface integral, every single part of the surface. So we split it up, just like before, end cap, barrel. And what is this? Well, this is just EA. Okay, does that make sense? Okay, so this is an EA. And what's this? And what's this? 0, because they're perpendicular, right? They didn't show it, but it would, okay. So this is just 2EA. Okay, but now, you know, this equals Q enclosed over epsilon 0, right? Now, this is a plane. You know, so this is a plane. And we have a cylinder, you know, going through the plane, right? So where's the Q enclosed? What's the charge enclosed by the cylinder? Isn't it just a charge, you know, like right there? right? Because it's a sheet, right? It's a plane. That's the only charge enclosed, right? Okay, and then we know that eta is a charge over area. So that means that, just generally speaking, that means a charge is equal to eta times area. Well, so that means that the charge enclosed, is just eta times this area. And what's that area? It's just A. All right? And again, don't forget, if there's an A over here, you have to get, if there's some variable here that relates to the fake surface, you have to get rid of it. So if there's an A here, there has to be an A here so we can get rid of it. Okay, does that make sense? Anybody else? Please ask, because you're doing the rest. Any other questions? Adam?
This is probably a dumb one, and kind of, I was like skipping through. That's a P, not another group.
This is a row. Yeah, it's all Greek, man. Okay, any questions?
So when we did the wire one, we had to like find the components of A because we had to cancel like it out. Like I'm confused at why we had to find the area for the wire one, but not this one.
Okay, we didn't have an A in the wire one because it was a one-dimensional wire.
That explains a lot.
Okay. See, this is a two-dimensional surface, right? So there has to be an A. With the wire, remember, we're just treating the wire. I know that sounds crazy, but we're treating the wire as a one-dimensional thing. That's why there's a lambda, right? Because we only want the charge on the wire or the plane or the other. If the wire is one-dimensional, then we're going to use lambda, right? Charge per length. All right. I know this picture doesn't. It's kind of a misleading picture, right? But it's supposed to be a one-dimensional wire. Okay. I'm glad you're asking these questions. I mean, it's good. Any other questions? Okay. Do you think you can do it?
Sure.
Yeah. All right. Well, we're out of time. So Monday, you still have 2 to do, right? I said you do 3. So on Monday, I think we'll do one that uses rho. All right? Okay, so just practice. See you later.